Good morning, everyone. How's everyone doing today? Happy Wednesday. All right. Well, it's hard to believe, but it's the last lecture. So here we are. As always, just ask questions in the chat. And as another reminder, so again, this is our last lecture. And then on Tuesday or Monday, I'll probably still stream, maybe do a few review problems. So come ask questions, or of course, if you can't make it live, send me questions and I can go over them on Monday. So that will be kind of the last review session. And then the exam week has already been opened. So if you're eager, you can get started on that. All right, let's dive straight into where we were. And so we kind of mentioned this yesterday, that water can do this. So we did this auto ionization. So just a quick recap. We said, well, sometimes our water molecules are staring at each other and then one will attack the other. So the electrons attack, and then we make some portion of hydronium, which again is often abbreviated as H+. And then we also are left with hydroxide. And so that's what is also shown here, again, with the abbreviated form. And so now we're getting into pH. And so now it was determined, well, at 25 degrees Celsius with neutral water, they found that the concentrations of hydronium and hydroxide were equal. And they found that they equaled 1 × 10⁻⁷ molarity. And so now this is kind of hinting at our pH scale. And again, once we plug this in, we'll really see. And so then we have our product, our ion product of water. And so kind of as an aside, so I don't want to go too much into it, but I do kind of want you to know where this Kw came from. And so we have our Ka expression, which we said, okay, we have our acid, right? And it can make most simply H+, and our base. But then if we wanted to do, right, our Kb, that would be like if we take our anion, right? And then it reacts plus water to reform our acid. So Ha plus hydroxide. And so now we have our Ka and our Kb. And then we said we could write our equilibrium. And so we end up with Ka is H+ over conjugate base over Ha. And then that means, so for Kb, that's equal to hydroxide times our Ha as we have it here. And this could just be base as well. I picked this to match over A-. And so now we get, so if we do Ka times Kb, this is equal to Kw. And so let's prove that. So now I'm just plugging exactly what we said in. So times Kb, so OH times HA. And so the whole point of this is to show, well, all this cancels out. And so we're left with hydroxide concentration times hydronium, or H+, like I abbreviated. And so this is our Kw water product constant. And so this is where this starts to come back in. And so the important part that you guys need to take away is that we have this relationship that, again, hydronium times hydroxide concentration has to equal Kw, which for our purposes is always going to be 1 × 10⁻14. So this is at 25 degrees Celsius. That's what we're going to assume. And this is also known as our dissociation constant of water. And so we also want to notice that they have an inverse relationship. So as one increases, then the other decreases. And we'll, again, kind of put that into the math then for our acid-base solutions. And so now we can say, well, all solutions contain hydronium and hydroxide ions. Neutral solutions have equal amounts. So we're starting to get into, again, pH of 7. And then acidic solutions have larger hydronium than hydroxide concentration. And so that means that our hydronium concentration has to be greater than this 1 times 10 to the negative 7th. Then, of course, the hydroxide would have to go down appropriately. And then comparatively, basic solutions have a larger hydroxide than hydronium. And so hydroxide would then be greater than 1 times 10 to the negative 7th. So start with these. See if you can determine whether it's acidic, basic, or neutral. And so let's take a quick look at these. So post your answer in the chat. Otherwise, you can always pause, of course, if you need more time watching later. So looking at A, so we have 7.5 times 10 to the negative 5th. So that's bigger, right, than 10 to the negative 7th. So that's less small. So this would be acidic. Now B, 1.5 times 10 to the negative 9th molarity. So negative 9, and we're looking at hydronium again. So that is smaller than negative 7. So that should be basic. And then C, we'll notice that one happens to be 1 times 10 to the negative 7th. So that is neutral. Now, I will admit, right, this is not the easiest way to kind of compare things. And so let's get into more of it. So really, we want to calculate the pH. So this is normally how we can compare. And of course, we're starting to get into our pH scale. We can see that from our KW constant. So taking the log of that, that's where we get 14. And so our pH is equal to our negative log of hydronium concentration. And again, you want to practice plugging this in on your calculator. So we can take the negative log of, and let's just practice with 1 times 10 to the negative 7th. And so that should give us 7 for our pH. And so that, again, tells us why neutral pH is said to be 7. That's where our pH scale comes from. And so we can look at some substances here so you can kind of orient yourself. So your stomach acid, so that is primarily hydrochloric acid, we had said. So that is a pretty low pH of 1 to 3, so very acidic. And then limes and lemons are also very acidic. And so that's why, your dentist is kind of worried about those types of fruits wearing down your teeth enamel. So that can cause some erosion. And then we have soft drinks. So again, very acidic. So both from the carbonic acid and a little bit of phosphoric acid in there. Other fruits are pretty acidic. So plums, wines, again, same issue with the teeth. And then as we go into apples, peaches, cherries, those are now higher pH, so not as acidic. Then beer is 4 to 5. And then notice, right rainwater, little acidic is 5.6. Human blood is kept at a tight buffer, so that's going to be a pretty small range of 7.3 to 7.4. And then egg whites are slightly basic. Milk of magnesia, maybe you've taken this, you've had an upset stomach, so that's basic. And then ammonia is obviously pretty basic. And then, of course, we go to sodium hydroxide. And then note this formula. So in case you're not as comfortable with the math, right? So if you remember for math, you can get rid of our log here by taking everything to the 10 power. So 10 to the negative power pH, right, gives us our hydronium concentration. And then we take 10 to the power of our negative log here. So that gets rid of our log, leaving us with that formula. So that will help you go between, right, pH and then concentration. And so this is kind of the nice thing about this chapter is you have all these relationships. And then if you have hydronium concentration, you can get hydroxide from the Kw. And let's keep looking. And so again, here's our pH scale. And we see it goes from 0 to 14. Again, from our Kw constant, we saw how 7 was neutral. All right, see if you can calculate this one, and then we'll get into pOH. How are we doing? So let's look at A. So A should be pretty straightforward. So this one, right, we have our pH. So now we can say, well, pH is our negative log of hydronium concentration. So negative log of 1.8 times 10 to the negative fourth molarity. And so plug that in. And so the nice thing about pH is you can kind of guess what the pH should be based off the order of magnitude. So it should be pretty close to that. So I'm guessing we'll get, so we have negative fourth. So it should be around 3 to 4. And again, let's check that. So yes, and then you add a sig fig. So now 3.74 would be our pH. So we put 2 in, and then with our log, we get another one out. Now, what do we do with B? This one was a little trickier. We had to use some relationships. So what do we think? So I tried to give a hint, right? So I said, remember that we have our hydronium times hydroxide equals 1 times 10 to the negative 14th. And so let's go ahead and do that. So we have that relationship. So we know that those two multiplied have to equal, again, that Kw, which was 1 times 10 to the negative 14th. So let's plug in our hydroxide. And so that means we can solve for hydronium. So 1 times 10 to the negative 14th divided by my 1.3. Oops. Lost the decimal. 1.3 times 10 to the negative 2. And so now I get this for my concentration of hydronium. I got 7 0.7 times 10 to the negative 13. Let's plug that into our pH now. And that gives me a pH of about 12.11. And so now we can tell that this is basic. Questions? And so this is a good transition to pOH then. So we have our pH, but we can also say, well, let's measure the pOH of something. And the pOH is equal to the negative log of the hydroxide concentration. So that makes sense. And just like before, we can also go back and forth. And so then if we take 10 to the negative power of our pOH, we get our hydroxide concentration back out. And now we also note that their scales are completely backwards. So pH, we said the most acidic was 0, and then 14 was basic. pOH, complete opposite. So that means 14 is acidic and 0 would be basic. But now we get to the relationship. And so this goes back to our Kw product constant. So we started with this, right? We said hydronium times hydroxide equals Kw. And so then if we take the negative log of both sides, so of course, the negative log of 1 times 10 to the negative 14th simplifies to 14. And then this, so they split it out. So then if you distribute this, you distribute the negative, but then you add them together. So then you have negative log of hydronium plus negative log of hydroxide. And so that equals pH and pOH, right? That's what those mean. And so now we get our next key relationship. And so this is what's really nice about this chapter is you can kind of check and double check yourself because you have this formula. Now we have this relationship, which is really nice. So we can just add pH plus pOH equals 14. So that's useful. And we could have used that to solve B. So if we go back to B, well, now we can say, well, let's calculate the pOH instead. So negative log of 1.3 times 10 to the negative 2. Oops, sorry. And so that is my pOH. And now I can say, well, 14 minus this gives me my pH. And yes, we got the same answer. So very convenient that we can do that. That really helps us out. So let's talk buffer solutions. And so buffer solutions are just defined as any solution that resists a change in pH when an acid or base is added. And so it's important to keep in mind that, right, this is only a small amount. So eventually your buffer could be overwhelmed. And so it works by either your buffer neutralizes your acid or your conjugate base part, So the acid, so if you added acid, this would be neutralized by your conjugate base and you would end up making your acid. Or if you added a base, it would react with your conjugate acid and then make your conjugate base here. And then what you see is, well, then that gives us equilibrium from Le Chatelier's principle. So this could react, right? So then you do the reaction, but then it might go back to equilibrium, right? So then even though this is reacted, then this might go ahead and reform some acid again. So that is how it resists that change in pH. And so I kind of hinted at it up here on how you make it. But again, let's read. This is super key. So either it has to have your weak acid and your conjugate base. And so in this case, that would be, let's just take, for example, vinegar, but let's call it acetic acid. I'll write out the structure for a second. So acetic acid here. And then its conjugate base. So then what's its conjugate base? And so this is acetate now, or acetate ion. And so we could pick any acetate ion for its conjugate base. So we could pick sodium acetate, lithium acetate, potassium acetate. So you'd probably just pick the cheapest, which I would assume is sodium, but I would have to look, be sure. Or let's look at the other combination, or you could have the base, a weak base, and its conjugate acid. And so a good weak base, maybe not a good one, but a good example is ammonia. So we have ammonia, and then it's going to react with water, or let's just say it reacts with water or any proton source to make ammonium, right? And so that means that we need, so it said weak base, conjugate acid. So this is our conjugate acid. And so any appropriate salts would be like ammonium. I would pick chloride or bromide. And then I would actually not suggest fluoride. Does anybody know why? So I'll give a hint. So ammonium fluoride has a confounding factor in that fluoride is a basic salt. And we'll get into this a little at the end, but chloride and bromide are both neutral. And this goes back to this chart here. So, right, we said, well, we had our strong acids that completely disassociated. So that means that their conjugate base, right, their conjugate base cannot reform the acid. So again, going back to this statement, the stronger an acid is at donating a proton, the weaker the conjugate base is at accepting a proton. Very key there. So back to the ammonium chloride. So that would be appropriate, right? Because chloride is neutral. So then we're just worrying about that ammonium being our conjugate acid to our buffer. Same thing with ammonium bromide. Bromine or our bromide ion is neutral, so no effect. But if we had picked fluoride, then we would have our confounding factor that our fluoride can also reform HF. And so that might not be good for our buffer system, right? So that would cause some confounding factors. Now, that being said, right, you might be in some sort of research situation where you would want to have a lot of some system of buffers, but that is not what we're discussing right now. So we're just keeping it simple. Want to pick an appropriate salt that does not have, any other influences. So a neutral counter ion for our conjugate acid ammonium. And so other examples is blood, of course, has a little bit of dissolved CO2. And then we have carbonic acid in there. And then also bicarbonate ion. And so this walks us through how we would actually make our buffer solution. So we would just do that by mixing our acid. So there's our acetic acid, and then mixing, again, conjugate base. So they picked sodium acetate. Again, sodium's just common. And so this is a little wordy, but all it's trying to walk us through is what reactions are going on. So let's say, so now we're looking at our acetic acid acetate buffer solution. And so it says if we add a base, then it reacts with our acid. So we can see that reaction, right? Neutralization reaction to give us water. Then we form our sodium acetate, right? So this is just our conjugate base, aka our salt that we put in. And so again, Le Chatelier's principle, even though reaction goes, makes our salt, but then we have some of this that can reform our acid from Le Chatelier's principle, right? Because adding this has stressed our system. We've made a lot of product, and then it's going to want to go back to equilibrium and again reform some of our acetic acid. So that is how our pH either increases slightly or not at all. And keep in mind what I said earlier, that we can't overwhelm our buffer, right? So you have a limit. So obviously you can't neutralize it all and have a large excess. Then, our buffer can't keep up. And so same thing, what happens if we add acid? We can take our same buffer scenario, and this time our acid reacts with our conjugate base, so aka that salt we put in, sodium acetate, do our double displacement reaction again, and so we get sodium chloride, and then also make our acid species. So now this is our HA. I guess I should have called this A as well, A minus up here, just so that's clear with my HA and A minus notation. And so again, Le Chatelier's principle, you have your reaction, you make a lot of this acetic acid, but then some of it might go back and reform, right, our sodium acetate, because it's always in that equilibrium. So it always wants to go back to equilibrium. And so that means our pH, again, will be a small increase in our pH or not at all. And I mean, increase acidity, so number numerically go down. And so that's kind of this text here. So again, we're saying we added some base to our acidic buffer, it neutralized it, and then we shift equilibrium. And then it just kind of repeats that scenario. And so the next question is, well, how do we calculate the pH of our buffer? And so for our purposes, we're going to use this equation, our Henderson-Hasselbalch equation. And so we say that our pH is equal to the pKa of our weak acid. So again, this is for weak acids. So it has to be our weak acid and then our conjugate base salt. So that's what we're referring to for our pH. So then we need the pKa of that acid. And then my formula says plus the log of the base over acid. So you might see alternate forms where it's pH equals pKa minus log of acid over base. So just watch for that. That's why you're going to see kind of two different forms potentially if you look around at other sources. And so for us, so this is talking about relationship derived from Ka. We don't really need to know where it came from. Again, just for our purposes, we want to be able to plug it into this formula. And yes, this X is small approximation is true. And for our purposes, we're always going to assume it's true. Otherwise, we have to get into more. I don't want to say it's that more complicated, but it's just not the focus of this class. So if you want to get into the more detailed math, that'd be my 200 level class. All right, so our last bits. So let's go through classifying these salts. And so we kind of talked about it, but we'll go through it. And then the last little bit of this, if we don't get to it today, we'll hit it up on Monday. And actually, let's just talk about it now, because what we'll want to do on Monday is the math. And now we kind of have this as more of a formality because we've seen the steps leading up to this. We talked about double displacement reactions, and then that double displacement kind of turned into neutralization. And so now this is essentially what a titration is we're doing a neutralization reaction, and then we're going to use different indicators to tell us when we've reached our desired endpoint, and that helps us calculate different things. And so let's just start with a simple distillation here. So this is one, I think we had the video on it, if I remember, for this class. So this should have been the last lab. And we have this titration. And so we have our base in our burette, so sodium hydroxide. And at this point, we would just kind of assume that we have calculated the molarity and that it's accurate. Then we start doing our titration. And so notice it turns pink. And so why that is because there's an indicator in there, phenolphthalein. And so this one turns pink at high pHs. So I think the threshold, let's look. Yes, we have the actual chart here. So if we go down phenolphthalein, and so it turns pink right around 9 to 10. So once our solution goes basic, and so for the purposes of titration, you want to catch it when it's really light. And so now check out these curves because these curves go pretty quick. Let's zoom in. And let's say you're titrating a strong acid versus a strong base. So boom, boom, boom. Look, you're really low. Then you're at the equivalence point. But look at how steep that curve is, right? So that's telling you that the pH changes really quickly, right? As soon as you hit that equivalence point, aka the number of moles. And so that's why it's totally appropriate to use phenolphthalein. And so then right after the equivalence point, it shoots up right away and our hydroxide is in excess. And then you might have, other fancy scenarios. So if you want to titrate, let's say a weak base and a strong acid. So notice this kind of has a gentler curve. So you might want to use different indicators. And so that's why there's this whole chart and family of indicators. And so, for example, thymol blue is a good diverse one. So it has a red coloration at a very acidic pH, then changes around 2. So it'd be orange around 2. Then you have, right, it's all yellow from this green. Now this is a pretty large area, right? So that's where you have to think about where is my transition, what's appropriate. And then notice it's green right around 8. And then it goes to dark blue past 9. So pretty cool. And so take this in for yourself. And this could also be an exam question. Hint, hint, is you might be given a series of indicators and it describes what color they are. And so you would have to refer to a chart. So let's say you said, thymol blue was yellow and methyl red was yellow. And what else? And nitrophenol is red. And then what might be the pH? And so, okay, well, thymol blue is yellow. So that's somewhere in this region. Methyl red was yellow. Well, that narrows it down, right? And so it has to stay below 8. And then it said nitrophenol was red. And so that matches with somewhere around the 6 to 7 pH region. So that's how you would approach those lab exam questions, is you're just trying to see when is that change. And, some of them, are green at certain pHs. So that's a big indicator or help. So just know where it's coming from. And so also note, so with these polyprotics, and this is where I'm saying you might need different indicators. So we won't worry about this too much in our class, but there are different Kas for a polyprotic acid, aka dissociation constants. I said I wasn't going to get into it. Now I'm getting into it. So let's just take phosphoric acid. Again, I won't get into it too much, but we have our first dissociation and then our next dissociation. And then For this one, write one more since it's triprotic. And so what this is saying, so this one is sulfurous acid. So this one, H2, so it has 2 equivalence points. But all we're saying is that, right, it's going to have 2 changes where we have one equivalent happen. Then you would see this shoot up. So that's also what it means by the equivalence point, is you have that rapid change in pH. And you have, again, this would be related to the Ka where this happens. Same thing with the second equivalence points. But again, we would save this for another class, probably not even like a Gen Chem series. This gets into more like analytical chemistry. And so that's super cool if you are interested and want to research more, but that's all we'll cover in this class. All right, so that's our quick and dirty of titration. And then the next step of titration would again be to do the math, like we've been doing math with our stoichiometry. Again, just relating it to solutions and solution chemistry. So there's our tie-in to our solution chapter. Well, let's go back to these classifying salts because this is kind of important. And so let's start with the first statement. So it says if the salt cation is a counter ion of a strong base, and let's start doing the analysis like I like to call it. So sodium comes from sodium hydroxide. So the answer is yes, it comes from a strong base. And what that is telling us, so it goes back to that statement. So now we're saying the equilibrium lies all the way to the right, so it's not going to reform, right? So sodium is not going to reform our sodium hydroxide in solution. It's always disassociated. And so that means that sodium is neutral if it comes from a strong base. And then, okay, let's look at the other half of this. And then where is it? And the anion is the conjugate base of a strong acid. Okay, again, what does that mean? So chloride, what acid does that come from? So HCl, so again, strong acid, completely disassociated. So that, again, our chloride can't reform HCl, and so that makes chloride neutral. And now if our cation and anion are both neutral, then we have an overall neutral salt. Let's just think about the analysis for calcium nitrate. So again, calcium comes from calcium hydroxide. That is fully disassociated ionic compound. And then nitrate comes from nitric acid. So that's also a strong acid. If you need help with these, go back to this chart over here, right? This is again reminding you, oh, there's my nitrate, right? It tells us does not undergo base ionization. So it's not going to reform nitric. So that's helpful for that section. Same thing with KBr. So K comes from potassium hydroxide. That's a strong base. Bromine comes from HBr, strong acid. So let's look at the next scenario. And so now it says if the salt cation is the counter ion of a strong base. Okay, so now we have neutral cation, right? That's what that's telling us. Let's look at all these examples. So sodium, yes, that's neutral. That came from sodium hydroxide. Same thing with calcium, came from calcium hydroxide. Potassium hydroxide. And now let's look at the next part. And the anion is the conjugate base of a weak acid. So there's a key point, conjugate base of our weak acid. And there we have it, fluoride, acetate, and nitrite. Again, if you need help, go back to your chart. So there's nitrite, there's acetate, there's fluoride, all telling us, right, that they can reform their weak acid counterparts. Again, let's go over what that looks like in solution for fluoride. So fluoride, and this is again a danger for a chemist. So sometimes, right, you might be doing a reaction that is getting rid of a fluorine and you might be making fluoride. And then what happens is it reacts with water. And so we said, yes, it does undergo ionization. So fluorine is a strong enough base because, again, it's from a weak acid, HF. So, yes, it is able to reform HF. We see it here. So there it forms HF. And now we see why it's called a basic solution, why it says it's a base, right? Because it says a basic solution will be formed. And there's our base. So plus we're left with hydroxide in solution. So definition of a base makes hydroxide ions. There we go. We proved that fluoride is a base. Same thing with acetate. So we could do the same scenario with our acetate ion. So it has the ability to reform acetic acid as well. So pluck off our proton, acetic acid, and then again, left with hydroxide once again. And so now let's look at the next scenario. And so let's skip. So if the salt cation is a conjugate acid of a weak base, let's go back to this thought. And the anion is a conjugate base of a strong acid. Okay, so that tells us anion is neutral. Now you might need some more colors. Getting crowded, right? So anion is neutral. But this is one of those ones where there's only so many examples. And so let's go back to this statement. The cation is the conjugate acid of a weak base. Well, there's only so many salt cations then. And so it has to be amine based. So we have, of course, our simplest, our ammonium. But now this could be any other amine variations. And if you've watched Breaking Bad, right, you could know that we have methylamine, which can then make methyl ammonium. So this is a methyl group. I'll draw in the CH3, so we know that's a methyl group. And then the rest of these, sorry, terrible 3D today. Let me try that again. Plane of the board, out of the plane of board, behind the plane of the board. There we go. So this is, I'll write it out, methyl ammonium. But right, getting the hint, it has to be, again, probably some sort of amine. And so those are your typical base salts that you're going to see. And so that's kind of what I'm trying to emphasize. Not a lot of possibilities. All right, now let's look at the last one because this is a little special scenario. And we have aluminum. And so it says if the salt cation is a highly charged metal, so that's mainly going to be like aluminum 3 plus or other metal 3 plus. And the anion is the conjugate base of a strong acid. So now nitrate, right? So now this is not going to have any influence since the anion is neutral. And so this is just something to kind of know. And so we had kind of said earlier, let's go back to our trends. Where are our trends? This trends in acidity. So we said cations are stronger acids than neutral molecules. So if you see these highly charged metal ions, again, like aluminum 3 plus, then that's a hint that it's acidic. Any questions about that? Oh, we actually went through that pretty quickly. Let's see. Looking for questions in the chat. Also going to look at your homework, just see if there's anything glaring. So again, reach out, ask questions. Let's see, trying to find anything difficult. Yeah, your homework actually doesn't look too bad looking at it because you don't have any stoichiometry problems. Note the formula. So, right, that's acid over base. That's why the homework has a different formula. But those are pretty straightforward. Same thing with these reactions. And then this is molarity. So I think you should be in pretty good shape for your homework. Let's try to find. I was trying to find a titration problem really quick. Need some inspiration here. Okay, let's try this one. So we titrated a 15 milliliter unknown HCl solution, so we don't know the concentration, with 17.08 milliliters of a 0.200 sodium hydroxide solution. And so what's the concentration of the unknown HCl? So take a minute for that. All right, let's go over this and see how we did or how it's going. And so maybe let's start off with writing out our problem just so we can visualize and have our balanced equation. So monoprotic acid, so 1-to-1 mole ratio, and we make water and sodium chloride. And so if they're in a 1-to-1 mole ratio, so now we have to figure out, well, how many moles of sodium hydroxide did we have? And I left off molarity, but I assume you knew what I meant. And so let's do that. So step 1, find moles of NaOH. So now we're back to our solution chapter. So we said, so 0.200 moles over liters. That's what molarities stands for. And then times, so we need to multiply it by our volume. But notice volume needs to be in liters. So multiply it by 0.01208 liters. So that should give us moles of sodium hydroxide we had in solution. And so I get about 0.002416. So that's moles of sodium hydroxide. And so now we're saying, well, it took, right, so there are this many moles of sodium hydroxide. So they're the same moles that are in our HCl solution. And so we need to get molarity, right? So now we can say sodium hydroxide moles equals moles of HCl. From our 1-to-1 ratio, I could have set up my conversion factor. And so now we can plug in molarity. So molarity is just moles over liters. Now we have that. So we have 0.002416 moles of HCl. We said it was in 15 milliliters. So just convert that to liters. My cat's gotten sassy. I think I said something wrong. I think I said 17 initially. Well, if you went with 17, you should get a different number. Now I apologize because I may have confused the audience here. And so if you ran with my typo, so I think I said one thing and then I couldn't read my own handwriting. So if you went with that number, you should get 0.161 molarity. And so let's go back. What if we had actually used what I had said originally, which was 17? So not a big deal. We can redo this. So times 0.01708. So that will change our moles. And so I'm just going to do, using 17.08 milliliters of 0.200 molar sodium hydroxide. And so redo that, plug in the math. And so now we get 0.003416 moles of sodium hydroxide, which is the same of HCl. And so now if I divide this number by 15, or 0.015, because we had to convert 15 milliliters to liters. And so I get about 0.228 molarity for our concentration. So again, depending what value you used, so I typoed later. So I used 12 down here and then redid it with 17 because I apologize for the confusion. All right, so that is probably, I'd say, next hardest math other than the Henderson-Hasselbalch in this chapter, which you have in your homework. Not too bad. You can plug that in. So I feel like I'm feeling good about this chapter for y'all. So reach out. Obviously, let me know if you have questions. We're coming to the end. I'll do a review on Monday, like I said, and kind of office hours. So ask your questions by email if you can't make it live, and I'll go over whatever topics you want me to cover. And just a quick summary. So again, chemistry is by nature cumulative. So your exam will just focus on the latter half of the material. You also have the practice kind of quiz. So that does not count for your grade, but it's just there to provide practice. So you can, again, kind of get a feel for the material and the questions. All right, reach out to me. I look forward to reading your emails, and have a great rest of winter quarter. Can't believe we're here. So keep it up. Enjoy your spring break, and I hope to see some of y'all maybe around campus or by email. All right, have a great Wednesday and the rest of your week. Bye. And I'll hang around on stream in case there are questions.